Gravitation potential energy. We know the gravitation force is a conservative force, so it has a potential energy. We will prove it, okay? This is coming from the assumption when R equal to infinity, the potential will set equal to zero, okay? UR, strictly speaking, it belongs to Earth and the particles, okay? But in our case, the Earth, the mass is so huge. So in this case, we can say, this is a particle's potential energy. If a system contains more than two particles, the principle of superposition applies. For example, we have three particles, and the potential is 1 and 2. It is M1, M2 over R12. 2 and 3, M2, M3, R23. 1 and 3, M1, M3, R13, etc. Now I improve this formula. The gravitation for potential energy equal to minus G M. This is the Earth's mass. This M is the particle's mass. This R is the radius of the Earth. We know the definition of delta U. The potential difference is defined as minus work done by this force. And this work equal to dW integration. What is dW? dW is F dot dr. In this case, F is into the center of mass. R is out to the center of mass. So if we assume R equal to infinity, the potential is zero, then we can calculate delta U starting from infinity to R. Okay? And look at the F dot dr. What is F? F is inside the world, okay? R is out. So the angle between them, cosine phi, is cosine 180, which is equal to minus 1, okay? Minus 1. And what is F? F is GMMOR, it's dr, okay? Now we find the delta U. Delta U equal to UR minus U0 initial. This is 0, so this is equal to UR. UR is what? UR equal to this one, integration. Okay? This is integration. This is integration. Integration is from infinity to R. This minus is from definition. This minus because F and dr in different direction. Okay? And we very easy find the integration. We take all the number G and R out. This is integration is minus R over 1. Very easy. We put the number inside, we get this answer. Path independent. Gravitational force is a conservative force. So the work done from A, B, C, D, E, F, G equal to the A, G, B, G. Nothing to do the path. Okay? The gravitational force is a conservative force. The work done by it on a particle moving from an initial point I to a final point F is independent of the actual path taken by the points. So delta U equal to U final minus U initial equal to minus W. This is the work done by the gravitational force. This is definition. Okay. So the change in delta U in a gravitational potential energy is also independent of the actual path taken, only depends on the two terminal ends. The potential energy and the force. We learned previously the force equal to potential energy dr minus. If you don't remember that, you go to chapter 4. We have this one. And in this case, we know the U. U equal to minus G m R. We do the derivative with respect to R. So we get R squared minus. This minus number, that means it is toward the center. Attractive force. Escape speed. If you fly a projectile upward, usually it will slow, start momentarily, and return to Earth. There is, however, a certain minimum initial speed that will cause it to move upward forever, theoretically come to rest only at infinity. And this initial speed is called the escape speed because the subject that can escape. Look at escape speed. Let's see the final situation. We set the final potential energy is 0. And in order to make the minimum total mechanical energy, we suppose the start at infinity just sit no speed. So in this case, at infinity, the total energy is 0. Also, because kinetic energy, mechanical energy, so the initial kinetic energy plus initial potential energy, this is initial kinetic energy. This is initial potential energy at the Earth. They should be equal to 0. So in this case, in order to escape, minimum energy we need is this m equal to 2gm or r squared rho. If we put this m as Earth's mass, this is Earth's radius, and we find this velocity about 11.2 kilometers per second. In order to escape from Earth to Moon to Sun, at least you need launch speed called escape speed, 11.2 kilometers per second. Sample. An asteroid headed directly towards Earth has a speed of 12 kilometers per second relative to the planet when it is a distance of 10 Earth radius from Earth's center. Neglecting the effective Earth's atmosphere on the asteroid, find asteroid speed v final when it reaches Earth's surface. Now this is a simple question. This is a mechanical energy conserved. See, at the 10 r distance, you have potential energy, and you have velocity. And at the surface of Earth, you have UF, then you can know its kinetic energy, okay? And you can find the speed. This is half m final speed we want to find. This is potential energy when you reach the Earth's surface. This is initially at the 10 r distance, the potential energy plus the kinetic depth. So in this way, we can find V final, okay? V final square equal to Vi square. Combine these two, get this one, we get V, okay? We put number inside, we get the answer. 16 kilometers per second, very huge number, very dangerous.